So here's the second fundamental theorem of calculus again. Just to summarize, if you take the derivative of an integral, you get the original function. Duh. But that only works if you have a definite integral that will be a function of x. There has to be a variable in there. If you have two constants, when you integrate, you get an area or a number, and when you take the derivative of any number, it's just going to be 0. This only applies to integrals that have a variable plugged in somewhere. But it should be a very simple and easy rule to go by. So, part A here, I have cosecant. Do you know what the integral of cosecant is? Yeah. Neither do I. Actually, I do. I'm just not telling you yet. But you don't know it, so that's okay. But you know that when you take the derivative of this integral, it's just going to be cosecant of x. When I take the derivative of this one, I could integrate it first, plug these values in, and take the derivative. Or I can say, you know what? Derivatives and integrals are inverses of each other. Whatever one does, the other one will undo. Try part C on your own right now. If you got an answer, the natural log of x squared plus 1, give yourself a pat on the back. Now, I just want to point out this last one is a little bit different. Take a look at where I put the variable. This has been set up where we have a constant going to a variable. The lower limit's a number, and the top limit is a variable. So what happens when I switch those around? Well, if I didn't know better, I'd swear we have a rule about that somewhere. If you want to, switch it right back, you just make it negative. Or you can just think of plugging this number into the antiderivative minus that one. You're going to wind up with the exact same answer, but it's going to be negative. Just make sure it is negative. Why did I bother to write all these terms in? Make sure it's negative. And that's as hard as this gets. Until it gets a little harder. Just a little. You see, it turns, you get a little bit of a change up going if it isn't just going up to a variable that is x. Sorry, that's hard to read. That is x squared up there. And I am just being difficult by saying, hey, this one's theta, d theta, u, du, and then t dt. Doesn't matter what variable you use inside. We just know we're going to plug in the variable that's one of the limits. And in this case, it's always x. However, if we took a look at this rule and we went through it again and we said, oh, you know what? We are integrating this. And then we take the derivative. Well, that's not too hard to do. But what happens if I had plugged in x squared? Well, right here, I get x squared plugged into my function. But when I take the derivative of that, we have something called the chain rule we must remember. If this is x squared inside my function, when I take the derivative of that, I have to remember to multiply by the derivative of the inside function. I have to remember to multiply by the derivative of the inside function. How does that affect all these wonderful little problems over here? Let me show you. All you need to do is plug in x squared, but by the chain rule, when you take that derivative, remember to multiply everything by the derivative of whatever variable you had plugged in. In this case, the derivative is 2x. In example F, you plug in your variable to the function. That's it, except chain rule. When you're doing the chain rule, when you're taking the derivative of this integral, what is the derivative of sine? So go ahead and try and do part G on your own now and see what you come up with. Make sure to square the 3